you solve for the Hamiltonian of the simple harmonic oscillator and say that the particle is undergoing motion according to Hamilton's equation, which we learned in the very first lesson, let me know that this should be very familiar to you. X of t oscillates like this. Okay, I can set the phase to be 0, let's say, so it's just oscillating in time, blah. And P of t, the momentum shows as minus m omega x naught sine omega. So this is clear to you what's oscillating, right? This is really back and forth. But what's really weird is that fundamentally we somehow found some weird spectrum. En equals to n plus 1 half h bar omega. Then there was this quantum Eigen states. There were wave functions that looked something like the ground state would look like this. And then the first excited state would look like this. What was it? I think like that. The next excited state looks like this, and so on and so forth. So, what's the link? I think if you have gone through the math, you'll follow either math, but maybe the physical picture might not be entirely clear. Okay? So here's where I want to answer the question for you. So let's think about what's happening in the classical mechanical case. We are looking at a particle and it's undergoing simple harmonic motion. And think about what a classical particle is. It's a particle that you can detect with arbitrary precision in momentum and space. It's a point particle. But as we learned in quantum mechanics, there's no such thing as a point particle. It has to obey the Heisenberg uncertainty principle. Right? Okay, so it's a bit fuzzy. But then you can use this notion to say, are some quantum wave functions more classical than other wave functions? For example, it's my choice on what to draw psi of n, psi of x. I can prepare the particle in whatever wave function I want to, as long as it's normalized and the area of the curve is 1. Suppose I draw this wave function like that. Okay, is this really classical? Well, what it is saying is that it is a valid wave function, perfectly valid. If you could prepare this thing, but you would work really hard to do it in the lab. And the reason is because this wave function is encoding information that you are detecting the same particle in that position and that position, roughly 50-50, right, if you look at this picture. This is kind of weird. You don't expect a single particle to be in 2 positions at the same time, right? So we can say that this wave function describes something very quantum, more quantum. Then, on the opposite end of the spectrum, what's less quantum? Or what's most classical? Well, something that agrees with intuition, it should be most tightly focused. And so it should look something like this. Right? Because it has pretty much well-defined position, not exactly well-defined, but pretty much well-defined. And if you look at the momentum space representation, and also it has some very well-defined momentum, a little bit of fuzz there, but it's okay. And so we would say that this is more classical. So we are led to come up with the criteria that we should search for wave functions like x. So this is our choice, right? We want to prepare the system in a way such that in this wave function, the Heisenberg uncertainty principle is saturated. You want this to be saturated. That means that we want it to have the least uncertainty. Okay, so now if I pose this question to you, this is a well-defined question. You can try to solve it. And this was precisely what Erwin Schrödinger tried to solve in 1926 or something like that. When he asked, I can quantize the theory, you can find all these eigenstates and eigenvalues, but so what? How does it connect to my understanding before of classical mechanics? Actually we have found one wave function that saturates this. Can anyone tell me what it is? No one? I mean, we've only calculated the Heisenberg uncertainty principle for a handful of wave functions, so it must be one of them. So which one is it? Is? No idea? No, I mean, look at the which ones, like the ones here.
And is equal to 1.
And what does energy equal to 1 mean?
So the first energy state.
0. So
Yeah.
the ground state.
Zero, yeah.
So we start from 0, we count from 0. So it's slide 0. Yeah, so the ground state is at equilibrium. And so it's centered somewhere, it's not moving, it's just stationary, it's Gaussian. And we calculated at some point, both from the wave function method, where I had to do integration by parts, and also last Wednesday by the raising and lowering operators. I calculated the entire set of variances, and we found out that the ground state of this wave function hits the Heisenberg uncertainty principle. So it's the most classical possible. Higher accelerated states are a little bit less classical, more quantum. But there's only one state, so that's not very nice. But let's understand what the shape of it is. The shape of it, the most classical one that we found it. This was this. E to the power of minus x squared over 2. Okay, I'm suppressing all the constants. I only want to care about the functional form. So it's a Gaussian. Okay? So the Gaussian is the one that's most classical, most tightly localized. But why can't I just shift it? Why can't I shift the Gaussian? Instead of having it be centered around 0, why not have it be here? Okay, so what does it describe? It describes a new wave function that looks like this.
Minus 6.
It's just a shift of the argument. Okay, so we should be looking for such solutions. These wave functions I claim will be the ones that saturate the Heisenberg uncertainty principle. And this was exactly what Schrödinger found. So he wrote down this. So Schrödinger said, I observe that the ground state obeys A0 equals to 0. And this should be, this has a meaning. It's not just an equation. It means that it's a vacuum state where you try to lower the energy of the particle and it vanishes. Because it's not going to go. There's no particles in that system. Okay? 0 is a vacuum state. He said, why not solve for alpha? Some state, he's going to call it alpha, such that A on alpha equals to alpha. I.e., an eigenstate of the lowering operator. Where alpha is equal to a complex number. Now, you've been used to the fact that eigenvalues are always real for you, and that's true because of spectrum theory, if your operator is a mission. But recall that the lowering operator is not a mission, right? So you can try to diagonalize it, and generally speaking, you get complex eigenvalues, and that's why you allow for alpha to be complex. So he's saying this: find this, solve for alpha such that you obey this equation. We know one solution. Alpha is 0, so that's a ground state. Now he's saying let's extend it, let's solve it, okay, for other kinds of alphas. And then, okay, so what's the solution to this? Okay, we can go through the math, but let me just state the solution, and then we can just check it. So the solution is going to be, it's a superposition over all the energy eigenstates n. So this n, here are the energy eigenstates n. And it's going to be some very particular linear combination. It's going to be this alpha n over square root n factorial n equals to 0 to infinity. And to make it single sum of mod alpha squared n over n factorial. But that's precisely the definition of exponential for the Taylor series. Okay, so therefore the two terms cancel out. That's just for the meaning of what exponential is. Okay, now let's check that it is an eigenstate of alpha A. So let's apply A onto alpha. Okay, so let's keep the normalization constant, and then the only thing it does is a lower n to n minus 1. But don't forget that if I apply A onto n, yes, I get n minus 1, but I get it up to a factor, right? This is what we derived last lesson. And the factor is square root of n. Don't forget this factor. So A acting on n gives me square root of n minus 1. Everyone remembers what factorial is? N times n minus 1 times n minus 2 times 1. So you see that since in the numerator I have an n, in the denominator I have n factorial, that simply shifts the factorial to n minus 1. Okay, so I can write this as e power minus alpha squared, sum n equals to 0, and then the, well, I guess this one, yeah, so now this should be 1, and then alpha n over square root n minus 1 factorial n minus 1. Okay, so that just shifts the factorial. But then we see that the sum starts from 1, a new sum. But why not I just start counting from 0 again? That means I just reshift my label. And so I shift n to n plus 1. Because it's just a relabeling, right? So it's a recount. But in doing so, I get alpha squared. N equals to 0 now. So I made it back to 0. Then alpha n plus 1 over square root of n factorial. And that's exactly the same as what we had before, except for this plus 1 factor, which is common to every term. So I can factorize it out. Blah, 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 blah. And then blah, 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 that's the same state itself. Right? So I'm calling the blah, blah, blah this. Because for every term, it has the same constant factor alpha. So I just pull it out, and then what's that? So we have found that it satisfies the equation. Good. Done. Okay, so what to say? Let me write it down and just tabulate the state. So we see that, so the solution is this. Pick any complex number, alpha. Then this state is going to be called the coherent state. We define the coherent state alpha as alpha equals to e power minus alpha squared over 2, sum n equals to 0 infinity, alpha n over square root n factorial n. Okay, so there's a terminology I just introduced. I just call it the coherent state. You may ask, why do I call it the coherent state? I think we'll see that, we'll see why. But for now, just, if you're not really following the math, just treat it as a very particular linear superposition of energy eigenstates. interesting are the properties of this state. Okay, so let's erase this. And let's erase this. And let's ask this question. What's the mean position within coherent state? In other words, what's the expected value of the position in coherent state? Okay. So we do the same trick. We express x as the linear combination of A and A dagger with the coefficients. So that's equals to square root h bar over 2m omega. And since I asked about position, of course I'm going to ask for momentum as well. So for good measure, let me just write it down. P is equal to A dagger minus A. Okay, so let's write that A dagger here. And then we divide by m h bar omega 2 times I. Right? Hopefully I didn't make any mistake here. And then with this, we can easily evaluate it. So what we want to do is we want to evaluate x, expected value. And that is inside the coherent state. So this is A plus A dagger times alpha times square root h bar over 2m omega. Okay, fine. But then we see that alpha is an eigenstate. So A acting on alpha gives you an eigenstate. And similarly, alpha acting on that is an eigenstate. So let me write it out. We know by definition that A alpha is equal to alpha and alpha. I hope you can see the difference in my handwriting between A and alpha. And therefore, alpha A dagger is equals to alpha star. So using that, we get that this is nothing more. Okay, so if I want to, let's work it out carefully. So this first term gives me alpha star alpha. Second term gives me alpha. But now the alphas inside the bracket are all numbers. So therefore, they can be pulled out because they're numbers. Don't forget, these are operators. But now since I use the eigenvalue equation, these are numbers. So numbers can be pulled out. And then all I do left is evaluate the overlap of the statement itself, which is 1. Okay. So therefore we get alpha plus alpha square root h bar over 2m. Okay. Now, since alpha is a complex number, I can always write it as its modulus and then e power pi theta for some theta. Okay, I can always write it. So it's a complex number. And then so alpha plus alpha star is not more than twice cosine omega. Twice alpha cosine omega times square root h bar over 2n omega. That's equals to alpha times square root 2h bar over 2m over m omega cosine a. Okay, so there's some non-trivial mean position, as it should be, but hopefully I'm shifting it to a new position, and that new position is there. That's the center of it. Okay, how about P? Okay, P, same thing. So you get that I square root m h bar omega over 2 alpha times a dagger minus a alpha. Okay, the only thing that changes is that this evaluates to alpha star minus alpha. Then we use a simple trig identity. Alpha z star minus z is sine of this argument. Therefore, this is alpha square root 2m h bar omega sine of a. How about the expected variance square? So variance square, we need to calculate expected x squared minus x squared. But everything just follows. Because this guy, okay, so let's concentrate on the first guy. We've already calculated the second guy. That is just h bar omega over 2n omega times alpha a plus a dagger squared. Agreed? And so if we expand it out, we get a squared plus a dagger squared plus a dagger plus a dagger a. But how do I do this calculation? Same logic. Since alpha is an eigenstate of a, and the bra alpha is an eigenstate to the right of a dagger, we can simply replace all the numbers, all the operators then, by just the classical numbers. This is alpha squared plus alpha star squared plus mod alpha squared plus. Okay? Okay. So you can work out this equation, this calculations, and then I guess what you'll find. Let's see, what's the best way to say this? The best way to say this is this. Okay, so now let's look at this left-hand side again. Left-hand side, mod x squared from this line, before I evaluate the last line, is, with the square on the outside, is h bar omega over m, omega 2 times alpha star plus alpha squared. And that is alpha squared plus alpha star squared plus what is it again? No, sorry. My bad. So here, okay, so let me slow down. Alpha star plus alpha squared gives me alpha squared plus alpha star squared plus twice alpha squared. Good. I made a mistake there. So I can replace everything by the complex numbers because this is the right order. So if I hit A onto alpha first, I get alpha star, then alpha, which is mod alpha squared. But I cannot do this. I cannot hit A dagger onto alpha because that's not an eigenstate. I need to swap the order. And the swapping of order happens and it expands the commutator. Right? And so now this guy indeed evaluates to twice that. And the last this to 1. Because this commutator is identical. So, very nice. Many things cancel out. We are trying to subtract off what we calculated from x squared. And we see everything cancels out. This cancels with this. And the only thing left is 1. So this is just h bar over 2m. Boom. Alright? Okay? Now, if I do delta p squared, same logic, you would find that this is equals to m omega over 2. Okay, I haven't shown you, but you have same logic, everything the same. Just keep track of minus signs and ion signs. So taking these two results together, we get delta x times delta p is equal to h bar over 2 in the coherent state. Okay, so what that means is that it behaves like the ground state, except that it's displaced from the origin. It's a displaced ground state. Okay? It retains its character as a very classical state. As what Schrodinger was trying to find. You know, he's trying to find what's the most classical state. Okay, we're almost there. Okay. So notice that this is true. This result is true for any alpha, right? For any alpha. I didn't care what the alpha was. It was always h bar over 2. And let me tabulate the result of x and p. Okay, x and p behaves like this. So let me tabulate x within the state alpha is alpha times square root 2h bar over n omega cosine theta. And then p is alpha square root 2m h bar omega sine theta. Okay? So I did some working. Working actually wasn't that difficult, actually. Everyone followed, right? It wasn't terribly difficult at all. You just have to know where to start, where to, equate things. Because in hindsight, I know where to do it, but maybe for first timers, maybe a few hours. At the end of the day, I've showed it to you that it's not that difficult. Okay? Now, here's the punchline. Let's talk about dynamics. Okay, so let's erase this now. So let's talk about dynamics. But we know what dynamics is undergoing dynamics by the Schrodinger equation. So we need to solve for the Schrodinger equation. And this is simply done by applying the unitary time evolution operator onto the state. Suppose I gave the original state. Okay? So the new state psi of t, let's call it new state, is the application of the Hamiltonian, the simple harmonic oscillator Hamiltonian, onto the alpha state. So that's the initial state. And that's my time evolution operator. Okay, that's all there is to it, but let's expand it. Let's use the definition of the alpha state. So first, let me just write the normalization. It's not too important here. Okay, so that's the normalization. Then sum of n equals to 0 to infinity over square root n factorial. And then the time conversion operator hits the energy state. Because all these anomalies, right? So it just passes right through, the operator then hits the state, and it's going to transform into a new state. How do we evaluate this? But that's an eigenstate of the Hamiltonian, and that's a function of the Hamiltonian. So this is an easy calculation to do. Since we know that Hn being an eigenstate gives you h bar omega n plus 1 half n. That's the energy En. So any function of the Hamiltonian, especially or particularly the exponential, is nothing more than applying the phase factor onto n. And in this case, it can be simplified easily to e to the power minus omega t n plus 1 half. Okay? So each eigenstate just picks up a phase, as it should be. So if you only begin from a single eigenstate, then phase is a global phase. It's irrelevant, you can't detect it, you can't see anything of it. But the coherent state is a superposition over different energy eigenstates. And then the phases start to matter because they are relative phases, right? If they're not global, right? Each one of them winds at different rates. So it's going to change the state somehow. So let's write it out. So we get alpha n over n factorial e to the power of I omega t n. And then I noticed that there's a 1 half here. The 1 half here is the same for any n. So that is a global phase. And I can factorize it. The ones with the n, I cannot pull out the sum, right? Because the sum depends on what the n is. This guy here, the 1 half, it's the same for every n. So I just pull it out. I know that it's global, so I can see it. Let me ignore it. But let me just leave it there for mathematical completeness. So I get a phase e to the power minus 5 omega t n because of that times n. But hang on, that's a complex number raised to the power of n. This is also a complex number raised to the power of n. So I could just define it as alpha e to the power of minus I omega t raised to the power of n over n factorial n. Do you agree with me? But what's alpha times e to the power of minus I omega t? It's a new complex number, right? So in the complex plane, think of it this way. If this is real alpha, and this is imaginary alpha, and let's say that I begin from some alpha here, multiplying by e to the power of minus I omega t, it's just going to wind it. So this new vector here is alpha e to the power minus I omega t, and this is alpha. The modulus remains the same, because as you can see, e to the power minus I omega t is modulus 1. So it stays in the circle, right? But where it is on the circle is changing, and it's winding around, it's a clock. So that this, in the complex plane, is moving as just a clock. This is where the simple harmonic oscillator is coming out, right? It's winding the clock. So we see that this time-evolved state, beginning from a coherent state alpha, is nothing more than a new coherent state. So it's again a coherent state. And this is the initial coherent state. story short, you became a coherent state, you remain a coherent state. All you're doing is just changing your parameter of coherent state from alpha to alpha e power minus omega t. Okay? This is the global phase, so it's not important. Global phase equals irrelevant, physically irrelevant. Okay? So when I write this equivalent, we dropping global phase. But let's look at the wave function of the state at time t. All the derivations, all the calculations I did before were for any coherent state. So we have again a coherent state. So what can we say about this new state in time for any time? It obeys, it saturates the Heisenberg uncertainty principle. Because our calculation was true for any alpha. So it's also true for alpha times e power minus I omega t. So which means that this new state in time is still very tightly localized. It's still very classical. It's in fact the most classical it can be. Okay, that's one fact. The second fact is, if I ask you, over time, what's the mean position of this state? Then you would say, oh yeah, I have to do this A plus A derivative. No, you don't have to, because I already calculated X for you and P for you within alpha, right? And this is true for any coherent state. So let me just substitute alpha is equals to e to the power minus I omega t in here. So now instead of alpha being this, you have in time, alpha t is nothing more than alpha times e to the power I beta plus omega t. Initially, it began with alpha. After some time, it does that. So this implies that the mean position in time behaves as 1 alpha square root 2 h bar over m omega cosine beta minus omega t, and the momentum behaves as alpha times square root 2m h bar omega sine omega minus omega t. And let's compare that to our previous classical understanding. This was done purely quantum mechanically. This was what you learned in secondary life. 3, 2, very simple. Yes. Very simple. Yes. You learned it very well. Simple numbers like this. And now we've learned it when you're, how old are you? 21? 20? 19? 22? 22, okay. Now you learn how to do it differently, but purely quantum mechanically. We see oscillations. We see that x goes so up to the side, it doesn't matter. It goes like that. Yeah. So if theta is 0, then you get something like this. And then this one. So it's oscillations. Wow. One more question. Yeah, I want to show you some simulations just to see, visualize it. Okay, since I gave it some time. Good. Let's erase this. Okay. One question you could ask is, great, I know that I should be looking at this state. That's my coherent state which is moving and it has this oscillatory behavior. What does it look like? What's the wave function of this guy? I know that it can be written as some, let's call this phi of x of t x. What is this guy? What shape is this? I'm saying that sine phi of x of t formally is written down as e to the power minus alpha squared over 2 sum alpha e to the power minus I omega t n over n factorial times the wave functions of the energy eigenstates, which are psi of n. And recall that the psi 0 looks like this. Psi 1 looks like this. Oops. Psi 2 looks like this. Psi 3 looks like this. And that's some function. It depends on t and x. For any given t, Uwe just said, well, this should be a Gaussian. Can you see the Gaussian? She's right. This is a Gaussian. But can you see that this is a Gaussian? This entire mad sum. Is this in shape? Looks like this.
Yeah.
Okay, so best to show you. I did it this morning. 10 minutes before class. So I thought it'd be nice just to show you this. Good. Okay. Let me explain what I'm trying to do. Okay. So I need a whiteboard as well. Okay. So ignore the screen for now. Let me just tell you what I'm doing. Okay. So I'm using this program called Mathematica. Very useful, symbolic program to do manipulations. You're not allowed to use it yet, because you're not qualified to use it. Only after you take a few more classes and you can. Because I don't want you to be doing this for using this homework for other classes. Right? You spoil the ability to solve equations or solve stuff. But I use it. Okay? Okay, so remember what we've learned. We say that we begin from the vacuum state. And that's given by the wave function psi 0. But how do we construct the higher excited states? We say that n can be obtained by applying the raising operator onto it. Okay? And the normalization was 1 over square root n factorial a diagonal n 0. So we apply it multiple times. Good. How does that help us? Okay, it helps us because you begin from psi 0, which is a Gaussian. So it behaves something like this, e to the power minus x squared over 2. And then now we need to understand what a dagger is in the position basis. How to represent it. So don't forget that a dagger was square root m omega over 2 h bar x minus plus I over square root 2m h bar omega p. Okay? So in wave function form, it's going to apply this operator. It's going to first multiply by square root m omega over 2h times small x. This is now a number. So it's going to give you a new function, small x times psi 0 x. It's a new function. And the p is going to be, so since p has this representation minus I h bar d by dx, it's going to differentiate by function. So one part of the A diagram is going to multiply by x. The other part is going to differentiate it by x. That's the action of the big X and the big P. But now we represent it in the position basis. Okay? So that is equal to plus 1 over square root 2m h bar omega d by dx. And then if you do it n times, so if you hit this new function with this, if you hit the functions with this operator many, many times, and you normalize it by n factorial, that should give you psi n of x. So that's a way to construct this wave functions. So in my numerics, I'm going to just simplify a lot. I'm going to set m equals 1, which means I work in units when mass is 1, omega is 1. So it just simplifies a lot of calculations. Then, in this case, under this scenario, psi 0 has a nice form. It's just 1 over pi 1 quarter e power minus x squared. And then this simplifies to 1 over n factorial, 1 over square root 2 times x plus 1 over square root 2 times d by dx of n psi 0 x. Okay, so first let's see that happen. So I've already done the calculations, but let me just run them through with you. Okay, so here's what's happening. First, I define psi 0 x. That's the first line. And then I just want to see visually what it looks like. So I'm going to plot the absolute value, mod square of it. The evaluate just is a function. I had to tell the computer the evaluate is a function. I'm going to plot it between minus 5 to 5. And then for good measure, I'm going to also integrate it just to check the area under the curve. So let me run it. Okay, let's run. Not surprisingly, it looks like Gaussian. And the area is close 1. That output, 5767. I've left my program on for very long, so there's done 6,000 calculations. Okay, now I'm going to define a diagram. For those of you who have some programming knowledge, what does it mean? So it means this. It takes in a function f, it spits out a new function, which is just a sum of two new functions. 1 over square root 2 times x times f. And then minus, I think it's a minus, sorry. Minus 1 over square root 2 d f of x. So that's just the symbolic way of differentiating. Let's just differentiate this. So if I define this function, so let me define it here. Just to give you a sense of what it is, let's do an A dagger acting on psi 0 of x. So that gives me x times the Gaussian, which is the Hermite polynomial of first order times Gaussian, which is exactly what we want. Then if we do it twice, then let's simplify it. Because the computer can do that for me. Nice. We get x squared minus 1 times Gaussian. You want to do it one more time? Okay. X times, so there's one more x in front of it, so it's x cubed, right? If I want to, let's just check whether or not this area of the curve is 1. So integrate absolute value of this guy, mod square x from minus infinity to infinity. Okay, let's just, oops, no. I didn't normalize the 1 over square root 3 factorial. So that should be that.
Wow.
Okay. 1.
What a great result.
Huh?
What a great result.
Thank you. Yes.
Yeah.
Okay, so now that I've defined this function, any wave function at 1. So I'm going to do a for loop, and I'm going to do 50 wave function. Why not, right? It's just here, what it means is that, look, n equals to 1 to 50, I loop 50 times, and then I just calculate the new wave function for the previous wave function by applying the diagonal onto it, and then I normalize it. And then for good measure, I'm going to show you some plots of what they look like. And then, first of all, this is the plot of the function itself. This is the plot of the function's mod square. And I'm also going to integrate just to see whether or not the area that goes 1. You know what, let me just do on the 20. Because it's too otherwise. So you keep doing blah, blah, blah. Okay. Eventually you finish. Okay, finished. Okay, good. So I've defined 20 wave functions. And let's look at what they look like. Okay, so let's look at the first wave function. Okay, that's psi 1. It's on as we figured out. I have drawn this multiple times. Psi 2. That's that. That's psi 3 and psi 4. So you can see what they look like. 3, 5. 10, okay, 20, look more like plane waves now. Okay. And if you want to look at the mod psi square, let's do psi square plots. Let's square it. So I'm just squaring this function, so everything should be positive now. And then this bump should go up. Okay, so it goes up. Psi 1 looks like that. Psi 5 looks like that. So on and so forth. Okay, fine. Everyone happy? Okay, so now we've defined what the wave functions are on the computer. Now I'm going to create a state. In fact, I'm going to create a wave function, this one. So I'm going to take each wave function that I've defined on the computer, and then sum it by the appropriate complex number raised to the power of n over square root n factorial, multiplied by the normalization. So here, I picked alpha is equals to 2 for fun. Why not? Okay. And I could have picked it with complex if I wanted to. And here's my sum. So if you know computing, you read this as, okay, ignore this first part. That's just the normalization. So I sum from 0 to 20. Okay, in principle, I should sum from 0 to infinity. But of course, I might as well just sum a few of them just to see what it looks like. So I sum from 0 to 20. Alpha to the power of n over square root n factorial, and then I define this function psi alpha. Evaluate, and I plot it. Okay? This is what it looks like. Okay. Let's do it step by step. Suppose I only keep one function. So I sum from 0 to 0. Then it looks a bit ugly. Then I sum 1. It's still a bit ugly. I sum 5. It's getting there. I sum 8. It's tending towards right shape. And sum 15. More or less is there. I mean, it's there. And 20, you can't see it anymore. And the orange curve, okay, so for any finite value, it's the blue one. The orange one is this function, the Gaussian, but shifted, with the center shifted by square root 2 alpha. Because don't forget, the mean position was this square root 2 times alpha. So the mean position is that. So for reference, the orange one is the perfect Gaussian, the blue one is the sum, and at the level where you sum over 20 wave functions, you can't see the difference. So we verified that the crazy sum gives you a Gaussian. Now let's see dynamics. Why not? Okay, here's what's happening. Let's define alpha to be twice e to the power minus I omega t. This is where is it? Yeah, this one. But I just picked a nice value for myself. Let's say alpha is equals to twice e to the power minus I omega t. Omega is 1 in this case. Fine. Not important. Like, you just change time space relation. And then I do exactly the same thing. I sum over that with the new alpha. And then I'm going to plot the mod square. I'm going to plot the mod square of this. And I'm going to manipulate, which means that I'm going to manipulate in time. I'm going to make a movie, basically, in time. Okay? And so here is, let's pull the slider to 0 first. Initially, this is what we saw before. It's all the way to the right. I think the spring is descended. Let it go is going to do this. See what's actually happening. This is my computer simulation of that theory that you have. Okay, so it's just going to oscillate, and you can visually see the oscillator now. This comes about from quantum mechanics. Okay. See, one last fact, nothing to do with the simple oscillator. I said that this function, the Gaussian, the one shifted, can be decomposed into all of these functions. It turns out that, of course, for some of you, it should not be a surprise. You take any function that you want, it can be always written as the coefficient times the lowest excited state, the C1, times the first excited state, C2 times the next one, and so on. How do I get C0s and C1s? That's a coefficient, right?
You
That's
just
just
scale.
nothing more than an overlap
Yeah.
of your choice of wave function with the basis states. So Cn is just defined as the overlap between my choice of wave function and I think it should be the wave function. Psi 0, psi n,
Psi
r,
NX.
phi 0.
The phi. Yeah.
And then the statement here is that this should be the sum of all the Cn's, psi n's, x. And let me just show it to you, if you just to visually see. Here's my test function. I don't know, I just found one. Just a unit triangle. It's a bit funky. Okay, it's minus 1 to 1 rises up. I'm going to decompose it in terms of this, this, and this. Now, first of all, visually, you can already say that most of it actually, this already captures most of the behavior of it. The rest are actually corrections to it. So then I'm going to calculate the coefficient table. I do that by doing this. I integrate the triangle times the wave function, precisely evaluating this guy. And then I get a list of numbers. And I can see how large they are. The first one is 0.7. So that means that the weight here is 0.7, which is the largest, as you can see. The second one is 0. And that makes sense because this is an odd function. The triangle I care about is an even function. So why the hell would you use an odd function to represent an even function? The coefficient of that is 0. So therefore C1 is 0, C3 is 0, C5 is 0, C7 is 0. And then you see other coefficients. This is psi2, psi4, psi6. And then I'm going to use the coefficient of this I've created, multiply that by the wave function at f, and let's do it slowly. Let's calculate, say, 2 wave functions. Okay, it looks like this. Okay, it doesn't look like a triangle yet. Suppose I sum 10 of them. It's getting there. Suppose I sum 15 of them. It's getting there. 25 of them. It's getting there. 35 of them. 50 of them. Okay. And let's compare this and that. Okay. So I'm decomposing my triangle into the eigenbasis of my harmonic oscillator. Okay, that's all I'll teach you, and you have yet to uncover many things in quantum mechanics, like solving for the energy levels of the hydrogen atom. But you can derive everything you want to know about the hydrogen atom. Levels, fine structure, everything like that. I've taught you a lot of stuff that is exact in quantum mechanics, right? But in real life, nothing's exact. So you need to know how to deal with non-exact solutions or theories in which, so you have to learn about perturbation theory, for example. And these will be the purview of other classes in the future. right now, this class is only teaching the very bare basics of it, but hopefully it has grounded you so that you can take those advanced classes, and I hope to see you in future classes. Okay, so we'll still have the tutorial after this, but with that, then I hope to see you around at some point in campus, and yes, thank you. So the PAs, please come and set up the tutorial, and those who want to stay can stay.